All right, so this lesson is for pre-algebra. Ms. Vaughn's class on January 20th. So if you missed classes on that Wednesday, this is the lesson that you want to look at. So we're actually going to start section 3.7, which is solving linear inequalities. There's just a couple of problems that I want to do as sort of a lesson opener to sort of wake up those brain synapses on some things that we learned earlier in the year. Before we get into the new stuff. So you can go ahead and open your book to page 120, but then I want you to always make sure you've got your notebook, extra paper and stuff ready. I will say, if you have any graph paper, that might help you because we're going to be doing some number lines. So if you need it, get some graph paper too. Otherwise, let's go ahead and get started. So let me share my screen with the whiteboard. All right. Is that blinking at me? Okay, so let's go ahead and get started. So these are not in your book. These are just some lesson opener problems I want to look at. This is for section 3.7. All right, so for number one, now in this case, I'm going to give you some equations. We're going to solve for x, and then I want you to think about which property of equality that we use to solve this. Remember, you have the symmetric property of equality, which means if you do something to one side, you must do it to the other. This is the basis for our equation solving. And then we also have the addition property of equality, and we have the multiplication property of equality. So for number one, we have x minus 3 equals 7. So we know to solve this, we need to add a positive number. So remember, we're adding the opposite to both sides. So we're adding a 3 here and here. So that gives us x equals 10. Now, in order to solve that, we have used the addition property of equality. All right, in number two, we have x plus 3 equals 7. All right, so again, I want you to think of this in terms of addition or multiplication. So we are going to add the opposite to both sides in order to isolate our variable. So I can write it for you like this so that you can see what I'm talking about. We're adding a -3, which is the opposite of a +3 to both sides. Now, we've also learned, though, that whenever you add a negative number, that is the definition of subtraction. So we really, when we solve these, we write that as -3, or subtract 3 from both sides, and x equals 4. However, if you kind of go back to the basis of what we were doing, we are adding the opposite to both sides to cancel out what's being done to the variable and then solve for that variable. So this is still the addition property of equality. Okay, number 3. So number 3 says 3x equals 12. All right, so let's go ahead and solve this. To solve this, all right, let me show you this again. Think of this in terms of multiplication. The opposite, or what we also call the reciprocal of 3, is 1/3, which is by definition division. Now, it's sort of multiplication and division, right? Because you multiply by the numerator and then divide by the denominator. But in this case, the numerator is 1. So the identity property of multiplication tells us that we can just rewrite this as 3x divided by 3 is equal to 12 divided by 3, which is what we normally do when we isolate our variable by doing the inverse operation. But you're still multiplying. You're just multiplying by the reciprocal, which in this case is 1/3 instead of 3. So then that isolates your variable. That becomes 1. and your solution becomes x equals 4. So in this case, we are using the multiplication property of equality. All right, number 4, just 2 more. So if we have x divided by 3 equals 12, well, the opposite of division is multiplication. And in this case, the reciprocal of 1/3 is 3. So we multiply both sides by 3. Again, x equals 36. And this one is much easier to see. This is the multiplication property. And I forgot how to spell it. Oh, so for number 5, the last one here, we have negative x equals 7. Now what do? We can't leave our variable negative because that's not isolated. Remember, if there is no coefficient next to your variable, it is an understood 1. Therefore, this is negative 1 times x equals 7. So to solve this, we multiply negative 1 by 1 over negative 1, which we write like this. Those negatives cancel each other out, and x equals negative 7. Therefore, we're still using multiplication property. Okay, so just to kind of refresh you on these properties of equality, let's look at solving linear inequalities. So if you remember from section 3.6, inequalities have an infinite number of solutions. You just have to figure out pretty much which direction on the number line you're going. Or in the case of a, x does not equal 4, then on the number line, you would include everything except the number 4. So if you look at example 1, they've asked us to graph, this is example 1, graph x greater than 6. So we would draw our number line. I'll throw a negative in there, negative 2, 0, 2, 4, 6, 8, 10. And then if we want to graph that x is greater than 6, and just a reminder of our inequalities here, we have greater than, we have less than, we have greater than or equal to, and then we have less than or equal to. So x greater than 6 does not include 6 because 6 is not greater than 6. It is equal to 6. So this is a false statement. Whenever a number is not included, but it is your starting point for greater than or less than that do not include an equal sign, you use, whoa, sorry about that. Let me fix this. You use an open circle, almost looks like a reticle, and then you draw your arrow in the direction that it's supposed to go. So when we graph x is greater than 6, we don't include 6, but we do show that that's our starting point. Then every number greater than 6, even if it's 6.00001, is going to give us it's going to be higher than the value of just 6. And so that would be our answer. Now, if we look at example 2, so this just gives us the option with the equals. If I'm asked to graph x is less than or equal to negative 3, then I would draw my graph. I got my 3, 0, negative 3, negative 6, negative 9, negative 12. We'll just make stuff up here. 3, 0, negative 3, negative 6, negative 9, negative 12. You can draw these however you want. You could do 1, 2, 3 and go down, whatever you want to do. But in this case, x is less than or equal to negative 3 means that we're starting at negative 3, but we're also including negative 3 because equals to is part of that inequality sign. So when that's the case, it's a shaded circle. And then you would point the arrow to the smaller numbers, anything smaller than -3, but also equal to -3. Okay. And then the last one I want to show you, or that they show you in the book here, is example 3 is when you have is not equal to. So you have x is not equal to 2. So when we draw that on a number line, sorry, I cannot draw a straight number line to save my life. 0, 2, 4, 6, -2, -4, -6. All right, then it means that x can be anything except net 2. So 2 is not included, therefore it must be an open circle. But then it could be anything greater than 2. And it could be anything less than 2. Because all of those things are not 2. Okay, so let's look at the addition property of inequality. And this is showing right there on page 121. If A and B are real numbers, so remember back to that Venn diagram, real numbers are all numbers from rational down to natural and includes irrational numbers, as long as A and B are real numbers, such that A is greater than B and C is also a real number, then A plus C is still less than B plus C. So let's say that A is 1 and C is 3 and B is 2, which is bigger than 1, and C is still going to be 3. So 1 plus 3 is 4. That's still going to be less than 5. So no matter what these values are, they will hold that A plus C must always be less than B plus C because A is already less than B. Okay, anyway. So we're going to use that to solve different inequalities. Let's see. Let's go ahead and do skill check 1. This is on the kind of in the middle of page 122. So skill check 1 asks us to graph a couple of inequalities, and then we're going to solve and graph some solution sets. So if we look at number 1, then we see that x is less than 7. 2 tells us that x is not equal to -4. And 3 tells us that x is greater than and equal to 0. So these 3, I'd like for you to pause the video. If you haven't already looked at this and tried these, I want you to pause the video and try these. Graph them on a number line and then start the video back up and see how you did. All right, so for number 1, line graph, x is less than 7, so I'm gonna, I don't know why. I'm gonna make this an 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, so if x is less than 7, that means it starts there, but it does not include it. So we do an open circle at 7, and then we draw our arrow all the way down to any number smaller than 7. All right, so if we have x is not -4, then I'm going to put -4 in the middle. We'll go -5, -6, -7, 3, 2, 1, 0. All right, so we start at -4. Now x includes everything but -4, so it's an open circle. And we draw an arrow up and down to include everything to infinity in both directions on the number line, except for -4. All right, last one here, x is equal to or greater than 0. Negative 1, 0, 1, 2, 3, 4, 5, 6. 1, 0, 1, 2. All right. So in this case, x is equal to 0. So our beginning spot is included. So it's shaded through. And then it's going to be anything on the number line. So pretty much any positive number or variation thereof is going to be included. Okay. So let's look at number 4 and 5. So number 4 asks us to solve and then graph y minus 12 is greater than or equal to negative 15. And then for 5, we're given negative 2 is greater than y plus 5. So, sorry, I'm checking something in the book real quick. Okay, excuse me. So just you solve back and forth across the inequality just the same as you would with a equal sign. So just the way we've been solving our equations, you would do the same thing with linear inequalities. So again, you want to isolate your variable. So y minus 12 is greater than or equal to negative 15. To isolate y, you need to add 12 to both sides. And we know that, so the sign stays the same. Y must be greater than or equal to negative 15 plus 12, which is negative 3. So this is our solution. Now we need to graph it. So what this is telling us, that the value of y must be equal to or greater than negative 3 for this original statement to be true. So we put that on the number line. And we are starting at negative 3, and then we're going up. So negative 4, negative 3, negative 2, whatever. Negative 4, negative 3, negative 2, negative 1, 0. 1, 2, 3, 4, 5. All right, so y is equal to negative 3. So we include the negative 3, which means that's shaded. And then it can be any number on the number line that is greater than negative 3. And we've graphed it. All right, so let's look at number 5. Again, we're isolating our y, our variable here. So to get rid of the positive 5, we must add a negative 5, otherwise known as subtracting. And so we end up with y must be less than negative 7. Now, when you flip your expressions and equalities, you must also flip your sign. So if I said, let me show you this. If I said A is greater than B, then I cannot say B is greater than A. This is false. What I have to do if I switch those, if I would have to say B is less than A, which makes sense logically, right? If A is greater than B, then B must be less than A. So if we wanted to switch this, because like I said, mathematical rules of etiquette say that your variable is always on the left of your equal sign, or in this case, your inequality, and your value is on the right. So to flip this, you would say y is less than negative 7. And we'll talk about this more once you're back in class if you have any confusions about this. So now let's go ahead and graph it. Make a graphing line. Now, y must be less than negative 7. So we're going to start with our 9, 10, 11. So we have negative 6, negative 7, negative 8, negative 9. Give it a good range. It doesn't have to be crazy long, but we need something here. Okay, so y is less than negative 7. That means that y cannot equal negative 7. So we start there, but it's not included. So that means that any number on the number line smaller than negative 7 is included, will make negative 2 greater than y plus 5, will make it a true statement. Okay. All right, so that's all we're going to do as far as the lesson. What I would like to do is look at some of the homework exercises. And we worked these together in class because it's Wednesday and we have Bible study or a youth group on Wednesday nights. We don't have any homework. So let's go ahead and go to page 124 and let's look at 2 through 12 even. I think that's what I had us do. Yeah. All right, so this is on page 124, numbers 2 through 12 even. All right, so number 2, in this case, we are graphing the following inequalities. So 2 is x is less than negative 2. So graph it. You're going to start with a negative 2 somewhere near the top there. So negative, we'll start with 0 here. Negative 1, negative 2. Just go down to that one. All right, and it's not less than or equal to. So we start at negative 2, but we cannot include it. So this should be an open circle. And then you go left down the number line into the smaller numbers. All right, so number 4 gives us x is not equal to 2. So draw your little number 9. We'll start with 0, 1, 2, 3, 4. All right, so it includes every number but 2. So again, your 2 needs to be an open circle. And then it's every number smaller and every number larger. All right, number 6. So number 6 is x is less than or equal to 4. So number line. We'll start with 3, 4, 5, 6, 7. Wait, it's less than, isn't it? Let me do that the other way. 5, 4, 3, 2, 1. Okay, so we're starting at the number 4. Now, do we need to include it? Hopefully you said yes, because the equal sign is included. So 4 is included to make this a true statement. And then any number smaller than 4, because the x must be equal to or less than the value of 4. All right, number 8. So 8, 10, and 12 are just asking us to solve. We don't have to graph it. So we have x plus 4 is less than 2. So just like we do when we solve equations, we isolate our variable. In this case, we subtract 4 from both sides, and we get x must be less than negative 2. So in order to make the original statement true, x must be less than negative 2. You can always check that by plugging the value you just calculated into x right here and solve it. You would get negative 2 plus 4 equals 2, which doesn't work, which we understand because there's no equal sign there. But then if you put negative 3 plus 4 equals 1. That is definitely smaller than 2, therefore it works. All right, so let's move on to number 10. Number 10 says y minus 2 is less than negative 3. So go ahead and isolate your variable, add 2 to both sides. Y must be less than negative 1 in order for our original statement to be true. And then the last one here, number 12 says z minus 6 is must be greater, z minus 6 is greater than negative 4. It's our original statement. So what must z be? What value must z have in order to make this statement true? Let's add 6 to both sides. So z must be greater than 2 in order for that to be true. All right, and that's it for today. So hopefully I will have a chance to see you back in class tomorrow, but if not, I will continue to make videos so that you can stay on track with the rest of us. Let's see here. There we go. All right, and hopefully this has helped you out. The class seemed to really like this. It made sense to them, and I think it's very logical. This is a nice stepping stone as we move into more inequalities. But just jot down any questions or notes that you may have while you're doing the work, and then we can talk about it when you get back into class. All right, thanks so much. Bye-bye.